Okay, Chapter 4, Section 9, Antiderivatives. What are antiderivatives? Well, let's start by thinking about the following. Way back long ago, we learned addition. Right, so let's say, for example, we have the number 10, and we learned to add values to 10. So 10 plus 1, okay, we knew that was 11. And then 10 plus 2, we knew that got you to 12. And then 10 plus 3. Okay, so we got pretty good at addition, right? Later they added negative numbers and stuff. Okay, but we learned addition. We're pretty happy with addition. And soon enough, they introduced subtraction. So then we can kind of go backwards here and think about 11 minus 1 gets you back to 10. Or 12 minus 2 gets you back to 10, right? So addition and subtraction are opposite operations of each other. They're inverse operations of each other. They undo each other, right? You can learn to add something, and then you learn the process of subtraction to go backwards. You started with 10, you learn to add 1 to it. That gets you to this answer, and now you get that answer, subtract 1, and it gets you back to where you started, right? So in a way, these two operations undo each other. Okay, then you learn multiplication. And let's say we start with the base number of 3. So we say 3 times 2, that was 6. And then 3 times 3, that's 9. And 3 times 4, that's 12. Okay, so we learn how to multiply. And again, soon enough, they introduced division. Division will help me undo this process. So say we started with 3 and we learn how to multiply it by 2 to get to 6. Now we can say, let's take the 6 and divide it by 2 to get me back to 3. Or take the 9 and divide it by 3 to get back to 3. Or take the 12 and divide it by 4 to get back to 3. Right? So again, the operation of multiplication and the operation of division undo each other. They're opposite operations. They're inverse operations of each other. Right? They work that way. Next, let's think about squaring things. We learn how to square numbers. So for example, 1 squared, we learned that was 1. And 2 squared, we knew that was 4. And 3 squared, we learned that was 9. Right? Squaring. The process of squaring. And then, soon enough, again, we learn how to undo that process. We learn how to find square roots. Square roots. So now if we take the square root of 1, we know that's a 1. We take the square root of 4, that's equal to 2. And the square root of 9, well, that's equal to 3. Right? We're just thinking about the positive roots, the primary roots. So again, these two operations undo each other. The process of squaring, the process of taking the square root of something. They kind of undo each other. Right? So for that process, for that purpose, for example, we could learn more sophisticated operations such as this, some unknown variable a, and then we add 7 to it, but then we also subtract 7 from it. We know that these two cancel each other out. They undo each other and go, okay, well, this kind of undoes with that, and the answer is just x, whatever x is, right? Likewise, we could do the same thing with multiplication and roots. So let's say, let's just stick to the positive. Say x is definitely some positive number, so we don't have to worry about negatives in this context. So if we have x squared and then we take the square root of that, well, that's just going to be x, right? The root, taking the square root and squaring operations undo each other. And we can do it in the opposite order as well. Taking the square root of something and then squaring it is also going to be equal to x. Remember, I'm only considering cases where x is definitely a positive number. If we allow x to be negative, then we run into some issues, but we're not doing that right now. Okay, so I'm just simply pointing out that these two operations kind of undo each other. Okay, so with all this in mind, let's get back to antiderivatives. What are antiderivatives? Okay, so far this semester we've spent a lot of time taking derivatives. We're pretty good at it by now. So for example, if we had a function If we had a polynomial function like this and we wanted to take the derivative with respect to x, we know that this should be a pretty easy process. This is just going to be 6x to the power of 1 plus 2 times 5 x to the power of 4. And then we just simplify that just a little bit and get 6x plus 10x to the 4th power. Right, that's that derivative. We also know derivative with respect to x of something like sine of x to the 3rd power, like that. Thanks to our chain rule, we know how to take this derivative. The derivative of the outside function is going to be cosine, so this is going to be cosine of x to the 3rd power times, the chain rule says I also have to take now the derivative of the inside function. So we get a final result of cosine x cubed and then times 3x squared. I wouldn't want people to confuse this, right? So this 3x squared is not inside the argument of cosine. So typically we like to switch it around and put it out in front. So this is equal to 3x squared times cosine x cubed. Okay, let's do one more. How about the derivative with respect to x, d dx of, say, e to the power of 2 tangent x? Okay, so we know that, again, thanks to the chain rule, this is going to be equal to e to the power of 2 tangent x times the derivative with respect to x of 2 tangent x, which is equal to e to the 2 tangent x times 2 secant squared x. Okay, so these are all examples, really good examples of derivatives. So we start with some function here, and we're asked to take a derivative, right? So this is sort of our start, our starting point. Find the derivative of this function. We start here, and this is our answer. This is the derivative of that function, right? What we want to learn how to do now is how to go backwards. We want to be able to start here. So given this one right here, how do we go backwards and figure out the function whose derivative is equal to the given value? So you'll start here. This will be your question, and then you got to learn how to go backwards to get to that, and that'll be our answer. Right? So given 6x plus 10x to the 4th, find the function whose derivative equals to this. So we're going to have to go backwards and get to that. Same thing over here to these two. So again, this was sort of the given function. This is where we started. This was given to us, and we're asked to find the derivative. And then we do some work. We do some chain rule stuff. We simplify, cancel, reduce. And this was our answer. This was the answer to the question, what's the derivative of this function? And now we want to go backwards. So we're going to start off with this. This will be the given thing, and they'll ask us to go backwards. Figure out the function whose derivative equals to this. And, well, we have to figure out a clever way of undoing this process to get back to this answer. Good. And same thing over here. This was the starting point, and they asked us to find the derivative. And then we did some chain rule stuff, canceling, reducing, and we took derivatives. So this was our answer. This is the answer to the question, what's the derivative of e to the 2 tangent x? This is it. But now we want to go backwards. We want to say, well, given this, once we start here, given this function, what's the function whose derivative equals to this? This one right there. So that would be our answer. Good. Going backwards, reversing. The process of reversing is can be referred to as finding the antiderivative. Find the antiderivative. Good. So find a derivative. That's the green one going this way. Find the antiderivative. That's this blue one going backwards. Going in reverse. That's the antiderivative. So as you can imagine, a lot of this is just pattern recognition, right? If this is given to me, how do I know what the answer is going to be? Well, it comes from knowing your derivatives really well. Just like if you recall, if you know that, what is that? Okay, well the answer is 6. Why is it 6? Well, because I know my multiplication tables. Because I know that 6 squared equals to 36. That's how I know the answer to this one. Likewise, I won't be able to answer the antiderivative, the blue. I won't be able to answer it unless I know my derivatives really well, right? So you're constantly going to be in this sort of guessing and checking process and pattern recognition so that you can identify the function that you think will give you the desired derivative. And then you're always just going to be constantly checking to make sure that your guesses are consistent and that they're making sense. The one nice thing about this section is that you should always get the right answer, or you should never be wrong, right? Because if you guess something, you can easily check it. And if it's not working out, then you know it's wrong. So, try something else or, seek help. But there really shouldn't be a case where you get the wrong answer and you think it's right, but it's wrong, because you can always check your work very easily. Okay, let's try building up to some patterns with some very easy ones first, and then we'll build up to some harder ones. Okay, so here is our formal definition of a derivative. So a function capital F is called an antiderivative of lowercase f on an interval I if the first derivative of capital F is equal to f of x for all x in I. Okay, so for example, let's just jump into a quick little example. So let's say, for example, lowercase f of x is equal to x to the power of 2. F of x equals to x squared. Okay, so find a function whose derivative equals to x squared. Let's find the antiderivative. So the question would be find the antiderivative. Find an antiderivative of f of x equals to x squared. Okay, so we got to come up with some capital F of x function, right? That's our mission here, such that when I take the derivative with respect to x of that capital F of x function, the answer will be lowercase f, right? In other words, I want something such that when I take the derivative of that capital F of x function, the answer will be x squared. Okay, well, if we remember our power rules, when we take derivatives of a polynomial, remember the power rule says this: the derivative with respect to x of x to the nth power equals to n x to the n minus 1, right? We subtract 1 from the exponent. So if I want my final answer after subtracting 1 to have a power of 2, that should indicate that I want something here that has x to the power of 3, right? So again, this is kind of a guess and check process. It has something to do with x to the third power. And then that'll give me the right power, the right exponent, because I know that when I take the derivative of this, it'll bring down the 3, and then I subtract 1, right? So kind of guess that, and then we check it, and we take the derivative with respect to x of capital F of x. Well, that would be the derivative with respect to x of x cubed. And following the power rule, we know that that's going to be 3 times x to the power of 3 minus 1, which is 3x squared. So we're close. We're almost there, except I didn't want this 3, right? I just wanted x squared. I didn't want 3x squared. So we're going to have to adjust it. And the way I can adjust it is to come back over here. Remember, I'm just kind of guessing what the answer should be. And what I will guess is to introduce a fraction here that gets rid of that 3. I'm going to introduce this 1/3, right? So now when I want to take the derivative, so if this is my function, now I'm going to check it, see if it works. Well, there'll be an extra 1/3 here. I can pull that out, so there'll be an extra 1/3 there. And now this 1/3 does the job of canceling with that guy. And so this will be gone. And now we get exactly what we wanted. So that's our answer. Find an antiderivative of this function. After all this kind of work over here, we go, okay, well, here it is. F of x can be equal to 1/3 x to the third power. And if we check it, that's this process here. The derivative of this will be exactly equal to that. Okay, so that's the process of finding an antiderivative. However, notice that it's not the only answer, because note that if we let capital F of x equal to 1/3 x cubed plus 7, that's also going to be an answer. When I take the derivative of this function, I'm still going to get x squared. Let me zoom out a little bit more. Note that if I take the derivative with respect to x of 1/3 x cubed plus 7, that's going to be equal to the derivative with respect to x of 1/3 x cubed plus the derivative with respect to x of the 7. And we know that the derivative of a constant is just equal to 0. And well, we established the derivative of this is exactly equal to that. So this is going to give me the same result. That's going to give me an x squared. So this is a valid answer. Yep, that works. But so is this. And in fact, if some other person says, no, I know f of x could be equal to 1/3 x to the third plus 9, that's a valid answer. Or f of x, let's get really clever here. We could say that this is plus pi. Yeah, that works too, right? In fact, we can let it be any number at all as long as it's a constant, and it's going to give me a valid answer. So we can just represent the whole family of answers by saying where there's a plus c, where c represents any real number. Where c is any real number. Good. Notice that up here, this thing said find an antiderivative, right? So it didn't say find the only antiderivative, because there isn't a unique antiderivative. There's a lot of them. So if it says find an antiderivative, you got lots of possible answers. Take your favorite. Any one of these is a unique antiderivative, right? They all work. On the other hand, if you want to represent all of them, the family of answers, then we have to express it this way. Okay, let's just take the base case and see if we can make sense of this graphically. So if we have f of x equal to 1/3 x cubed, then the derivative function, which happens to be equal to lowercase f of x, is equal to x squared. Okay, let's think about the derivative. What is the derivative? The derivative is the slope of the line tangent to the original function at point x. Right, so let's look at a graph. Okay, so I graphed capital F of x here in Desmos, which is 1/3 x cubed. So this is the shape of it here. And if we want to think about the derivative of this function, we need to think about the line's tangent at every single point. So they look like this. Here they are. So as we travel along the curvature 1/3 x cubed, then this red line here represents all the tangent values. Now the derivative is related to this. The derivative is going to be an equation that gives me the slope of the line's tangent, right? So at this point, the derivative should be some large positive number, right? Because the slope is positive. And as I travel this way, the slope should get smaller, still positive, but smaller and smaller, but still positive, smaller and smaller, but still positive, until we get to 0. And then it looks like it's another small positive, right? The slope is still positive. Then a slightly bigger positive, bigger positive, bigger positive, bigger positive, bigger positive, and so on and so forth. Here, Desmos lets me see the slope there. So let's say I do capital F prime of A. Here, this is the slope. At this point, the slope of this red line, the tangent line, is going to be 4.9284, right? Desmos calculates it automatically. So notice that the actual point on the graph is in quadrant 3. Both the x and y coordinates are negatives. However, the slope is positive, right? Look at the angle of the tangent line is positive. And as I travel this way along the curvature, we pay attention to the slope over here. The slope is getting smaller and smaller and smaller. It's still positive, but getting smaller and smaller and smaller until it reaches 0, right? When the line is completely horizontal. Doesn't quite want it. There it is. There. So it reaches 0 right when it's horizontal. And then afterwards, again, we get a small positive, bigger positive, bigger positive, bigger positive, bigger positive, bigger positive, bigger positive. So if I was just kind of focused on all these slopes and I graphed all of them, they would give me the graph. Graphing them would give me the graph of the derivatives. And then if that graph had an equation, that would be the equation of the derivative function. So we can just graph it. So I'm going to say y equals capital prime of x and there it is. Let's not make it in red. How about green? Done. Okay, so the green represents the graph of the derivative of our function. In fact, it's also, well, we already know it, right? It's x squared. That's how we found this. It's x to the power of 2. There it is. It's x squared. Okay, so again, if I start over here, I see that it's some large positive number. So that's tracing this back up here. It's some large positive number up there. And then as I come this way, now it's going to be a smaller positive number. That's why the green function is decreasing. It's still positive, but getting smaller and smaller and smaller. Eventually, that slope reaches 0. The green reaches 0 right around there. And then the slope becomes a small positive, bigger positive, bigger positive, bigger positive, which is why that graph continues to go that way. Okay, so hopefully that looks familiar back from chapter 3. Graph, its derivative, tangent lines, how they're all related to each other. And notice that if I take my original function and just shift it down a little bit, let's say we put -1 here, just shift it down a little bit, then nothing has changed in terms of the angles of the tangent line. The tangent line still has a large positive number there, and it's smaller positive until it reaches a horizontal right around there, then a smaller positive, bigger positive, bigger positive. So the shape of the derivatives, the graph that describes all those derivatives, stays the same. That's why there is an infinite number of possible functions whose derivative is equal to x squared. We can also think of a new one. Let's do different ones. How about -3? There's another one, right? It's the exact same graph. Doesn't like that. Let's do G there. Right, so this one also has the exact same shape. So as long as it's got the exact same shape, even if it's been shifted up or down or to the right or to the left, it doesn't matter. The shape will, as long as the shape stays the same, then the tangent lines will have the same slopes, which means their derivatives will be the same, right? We can also shift it up. Let's make this W, and then let's make this a plus E. Ooh, didn't like that. Where'd it go? Oh, there it is. But let's get rid of green. Green is our derivative. About orange. There we go. Okay, so the orange one, again, it's got the same shape. So for all of these ones here, it's a lot of colors running around, so let me get rid of this. So for every single one of those graphs right there, its derivative is going to be x squared. This green one will represent the derivative of all of them. Okay, so if we just leave it in general, then I'm not digging the orange. So if we just leave it in general, then oops, let's. So if we just leave it in general, then we can see that we can always just scoot this up and down by letting this constancy be any number at all, any real number, and we're always going to get a graph that has the same derivative. Right? Just shifting it up and down will give you the exact same derivative. Okay, so hopefully that convinces you that there's a whole family of functions whose derivative equals to this particular one. Your author actually provided a nice graphic for this, so remember that if f of x is equal to x squared, then one antiderivative could be f of x equals to 1/3 x cubed plus 1, or another one could be f of x equals to 1/3 x cubed plus 2, and so on and so forth. So each one of these could represent one potential antiderivative. And just so that for notation wise it's not kind of fun that they all look all the same, so let's call this 1 and 2, that way they're actually different. And so in general we could say that if f is an antiderivative of a lowercase f on an interval I, then the most general antiderivative of lowercase f on I is given by this function, capital F of x plus c, where c is an arbitrary constant. Good. And we can see a nice little graph here depicting all the different functions. And again, if we think about the tangent lines like we just did on Desmos, all those tangent lines are going to have the same slopes for any particular input, right? So if x equals to a, let's say here, x equals a, then all of these graphs, supposed to be right above, right below a, all of these graphs will have a tangent line that's going to have the exact same slope at that point, right? So they're all supposed to have the same slope. And that's true for any a as we go back and forth on some interval I. Okay, so let's continue to build on this pattern. We saw that when we wanted to find the antiderivative of x squared, the answer was x to the third times 1/3. So let's see if we can establish a general pattern for functions that fit this form. So if we have x to the second, we already saw that f of x equals to x to the second. We already saw that then f of x equals to 1/3 x to the third plus c becomes the most general antiderivative. Okay, what if, on the other hand, f of x was equal to x to the third power? All right, so what's the antiderivative going to be? Well, again, thinking about kind of a guessing and check process, I'm going to think about putting a 4 there, because I know that when I take the derivative, I'm going to subtract 1 from the exponent, and that'll give me the 3 that I need. However, if I take the derivative right now, f prime of x, I know that that's going to be 4x to the third power. I don't want that 4 there. That's why we introduce a multiple of 1/4, so that when I bring down that 4, it'll cancel with this 1/4 and give me the desired outcome. Good. Okay, so then that's the general answer plus a constant. Okay, let's do one more. How about f of x equals to x to the fourth? All right, well, by now we see a nice, easy little pattern. This is going to be x to the fifth, and then we have to multiply it by 1/5 plus a constant. So let's establish a general rule then. If f of x is equal to x to the power of n, then capital F of x, the function whose derivative will be equal to that, well, notice the pattern. We always add 1. Right? From 2, we added 1 to get to 3. From 3, we added 1 to get to 4. From 4, we added 1 to get to 5. So this is going to be x to the power of n plus 1. And once we found that number, we knew we needed to divide by 1, or multiply by 1 over, and then whatever that was. So we have to introduce a n plus 1 there, plus c. Good, good, good. Notice that we always have to be careful not to divide by 0. So here, note we can't let n equal to -1. If we let n equal to -1, then we're dividing by 0. We're saying find the function, and the function is going to be something that divides by 0. So this process isn't going to work for that. Okay, so we'll deal with that separately. But we've established one general rule. If we are given something that fits this form, we can follow this process, this formula, to help me find the antiderivative. Right? So remember, all of these are the correct answers. So the question would have been, find the antiderivative. Find the antiderivative. Right? And this is the answer on this side, that way, that way, that way, in their most general form. Right? And then if we wanted to check, then the check is easy. All we have to do is confirm that when we take the derivative of this function, it really does give me that one. So it's the answer because when we take the derivative with respect to x of capital F of x, the answer is going to be x squared. Right? That's what's going on there. And likewise with the others. Okay. So coming down here, the derivative with respect to x of 1 over n plus 1 x to the n plus 1 plus c, well, if it is in fact the antiderivative, the derivative of this whole thing is just going to be equal to x to the nth, just as we expected. Okay, so this is one pattern for one type of situation we're going to run into. We're going to look at others. In order to understand those patterns, though, you have to be really good at derivatives, right? All of this is built on understanding derivatives really well. So let's take a quick little look at a nice table that comes from chapter 3 that has a whole lot of derivatives that we've been working with. So here's a nice little table that has some of the most popular derivatives that we've been working with. So of course we know our power rule, which we just established, or we just refreshed our memories. X to the power of n, the derivative is going to be n times x to the power of n minus 1. The derivative of ln of x is equal to 1 over x. The derivative of cosine of x is negative sine x. The derivative of e to the x is still e to the x, and so on and so forth. Okay, so keep these in mind as we proceed with this process of going backwards. If you're given secant squared x and they ask you to go backwards, find the function whose derivative is secant squared x, well, the answer is tangent x. And if you're asked, well, why? How do you know that? Well, because I know that the derivative of tangent x is secant squared x, right? So you have to know your derivatives so that you can understand how to go backwards. So having said that, here's a nice little table of antiderivative. Okay, so here's a table provided by your author in this book. So as I had just pointed out, for example, if you're given secant squared x and you're asked to find a particular antiderivative, the antiderivative of secant squared x is going to be tangent x. And why? Well, because I know that the derivative of tangent x equals to secant squared x. Okay. Likewise, we saw that the derivative of e to the x is e to the x, so the antiderivative is going to be e to the x. Okay, so study this table for a little bit. Here's the one we spent some time on. So if we have something to the power of x, x to the power of n, then this is the pattern that will help us figure out a particular antiderivative. And if we want the general antiderivative, for all of these cases, we could always just add a c, plus c, plus c, plus c for all of these cases, right? Don't forget that plus c if you need it. And then a couple of properties of antiderivatives. A constant times f of x is equal to a constant times its antiderivative. And addition, and we'll see subtraction, will also transfer over. Okay, let's look at an example. Okay, let's try some of the exercises. Let's start off with somewhere here first. How about just a straightforward one? How about number 4 to start off with? Okay, so the instructions were to find the most general antiderivative. And this is a nice polynomial. We can use our power rule in reverse. So this one should be easy. Capital F of x is going to be equal to, leave the constant alone, and then I know I need an extra power, so plus 1 in the exponent. I'm going to need x to the power of 6, right? Because I know the derivative will bring down that 6 and subtract 1, so that'll give me that 5. But I don't want that extra 6 there, so I'm going to multiply it by 1/6 minus, leave the constant alone, times x to the 5th power times 1/5 minus, leave the constant alone, 9, space there, x to the power of 3 and then 1/3. Right, so in each case, the 3 comes down, cancels with a 1/3. The 5 comes down, cancels with a 1/5. The 6 comes down, cancels with a 1/6. Each time we reduce the exponent by 1 power, and then we'll have all those powers that are there. Okay, so the last step here is going to be to reduce it as much as possible. This goes in there 3 times. And don't forget to add your plus c to make it the most general form. So my final answer is going to be x to the power of 6 minus 8/5 x to the power of 5 minus 3x to the power of 3 plus c. Okay, let's try another one. Okay, let's try something like number 12. Okay, so again, we're asked to find the most general antiderivative. But before I jump into finding the antiderivative, I'm just going to simplify this a little bit. I'm going to rewrite it as f of x equals to x to the power of 2/3 plus, and then this is going to be x times x to the power of 1/2. And so if there's nothing in the exponent, by default there's a 1 there, and I know I can combine those two. So f of x equals to x to the power of 2/3 plus x to the power of 1 plus 1/2. Common denominator is going to be 2/2, which gives me 3/2. So f of x equals to x to the power of 2/3 plus x to the power of 3/2. Okay, so now that I have it in this form, this is very similar to the one we just did. Let's find the most general antiderivative, capital F of x. This is going to be equal to, okay, well, we know that the pattern is going to be to add 1 to the exponent, plus 1. And then once I figure out what that is, I know I have to multiply a 1 over that same number. Now you could copy it here like this and simplify it in a second. And again, over here, we're going to have x to the power of 3/2. And again, we add 1, and then 1 over, and then that same number. Okay, so we need common denominators. So instead of a 1, we can think of this as a 3/3, which then would give me 5/3. So this is going to be 1 over, and this is going to be equal to the same number as that one. So this will be 5 divided by 3, x to the 5 divided by 3. Right. If you want, you can also change it here. So this would be 3/3, common denominator 3, so that would be 5/3. Good. So remember, it's in the denominator, like that, plus 1 over something. Again, we need a common denominator. Let's make it a 2/2. 2/2 there, and then 2/2 there. So that'll be 5/2. 5 divided by 2, x to the power of 5 divided by 2. Again, this is in the denominator. So finally, to simplify, we multiply the numerator times the reciprocal of the denominator, which means we just flip this upside down. And that'll get us to our final answer. Capital f of x is equal to 3/5 x to the 5/3 plus 2/5 x to the 5/2. Now they did say find the most general form, so we have to, introduce that plus c. Don't forget about the plus c, and that'll be our answer. And the great thing about this section is that you can easily check all your work, right? So it's not necessary, we're done, that's our answer, but now we can check it. Let's check to make sure it's true, check it. So if it does work, in fact, it must be that when we take the derivative with respect to x of this function, it should give us that one, right? That's what we need to confirm, that the derivative of this function equals to f of x, right? Let's check if that's true. So the derivative with respect to x of 3/5 x to the 5/3 plus 2/5 x to the 5/2 plus c. Okay, so this is going to be 3/5 times, and now when we take derivatives, we bring down the exponent and subtract 1. So this would be 5/3 x to the 5/3 minus 1 plus 2/5 times 5/2 x to the 5/2 minus 1. And the derivative of a constant is 0. Now, luckily, all these fractions cancel. 5, 5, 3, 3, and 2, 2, 5, 5, right? Very cleverly selected fractions that cancel out. And when we get a common denominator here, this is going to be a 3/3. And over here, this will be a 2/2. So we end up with x to the power of 2/3 plus x to the power of 3/2. And that is, in fact, exactly equal to what we expect. This is the cube root of x squared plus x square root of x. So it worked out, confirmed. We found the most general antiderivative, and we can confirm that when we find the derivative, when we take the derivative of this function, it gives us exactly what we started with. Okay, how about something like number 18? Okay, so find the most general antiderivative of this function. Now at first this looks like it's kind of a hard question. How do you know what it is? But it's really not that bad. So lowercase g, so we're going to use capital G. So capital G of v is going to be equal to a function whose derivative is cosine. So remember, the derivative of sine is cosine. So this is just going to be 2 sine of v. Right? And that just comes from me knowing that the derivative of sine is cosine. Okay, and this one, again, that looks really ugly until you remember the derivative of sine inverse. So if you remember your derivatives, you can reference a table like this. And if you recall, the derivative of sine inverse x is equal to 1 over the square root of 1 minus x squared, then we can conclude that the antiderivative, going backwards, given this, the antiderivative would be sine inverse. Well, that's what we have here. So just by knowing that, I know that this must be minus 3 sine inverse of v. So it's both easy and hard, right? If you remember the derivative, then you can easily do the antiderivative. Now, if you don't remember that, then that's almost impossible, right? If you don't know that the derivative sine inverse equals to this function here, then there's no real way to go backwards, right? Just like square roots, the square root of 49. If you don't know your multiplication tables, you're not going to know what that is, right? So you have to know multiplication tables. You have to be really comfortable with it, and you have to just be able to spit it out. The answer is 7 because we know that 7 squared is 49. If you don't know that, then you don't really have a real good way of finding that. So if you don't know that the derivative of sine inverse v equals to 1 over the square root of 1 minus v squared, well, then you won't really have a way of finding this answer. Okay, so take time to remember these derivatives, memorize these derivatives, and practice. Okay, so now we just add our extra plus c to make it the most general antiderivative, and box that up, and that's our answer, right? This represents a family, because of the c, a whole family of functions whose derivatives are going to be equal to this one. Okay, so now let's work with some of these higher order derivatives. How about number 30? So we are given the third derivative. Third derivative of t equals to the square root of t minus 2 cosine of t. And our task is to find the original function f. Okay, so first of all, I hate working with the letter t, lowercase t. For me, in my handwriting, messy handwriting, they end up looking like plus signs, and I don't like that. So it's just a dummy variable. Why not change it to anything you want? So I could rewrite this in, say, the letter w equals to the square root of w minus 2 cosine of w. And it's the exact same question, so I can just work with w now. Of course, the most popular letter to work with in math is x, so I could just go back to x, and same thing, right? Okay, so I'm going to work with this one. Now, remember, our goal is to find f. Find f of t was the original question, but now we're changing it to x, so find f of x. Find f of x now. Okay, so we're going to have to go one step at a time here. The given function here, notice it's the third derivative. So when we take an antiderivative, we're going to go one layer back and go to the second derivative. So we'll say that the second derivative of this function, well, okay, this is equal to, well, you know what, let me just take one more step. This is the third derivative. I'm going to stick to 3. And that's going to be x to the power of 1/2 minus 2 cosine of x, just rewriting that there. And now the second derivative of x, well, that's just a very simple rule here. That's just going to be x to the power of 1/2 plus 1. And then this is going to be 1 over 1/2 plus 1 minus 2. And now the derivative of a function whose derivative is cosine, well, that's just going to be sine. Derivative of sine is cosine. Good. And, of course, we have to throw in that plus c. Okay, so now we simplify it, and we say that this is the second derivative of x equals to, now if we get a common denominator here, let's make that a 2 over a 2. That'll make it a 3 over 2. So this would be 1 over 3 over 2. X to the power of 3 over 2 minus 2 sine x plus some constant. And then we can simplify that. Second derivative of x then equals to 2 over 3 x to the 3 over 2 power minus 2 sine x plus some constant. Okay, so we've gone from the third derivative down to the second derivative. Okay, so let's take a minute here and box up what we have so far. We started off with the third derivative, that's this guy right here. And then after a bunch of work, we're able to get it back down to the second derivative. That would be this guy right here. So we're going to take it to the next level now. Okay, so now let's find the first derivative. So now the first derivative is going to be equal to some function whose derivative is equal to this. So it's going to be this constant, we leave it alone. And now we got to multiply this by x to the power of 3 over 2, and then we add 1 to the exponent, plus 1. Now that plus 1, we can rewrite it as a 2 over 2, which means that we'll have 5 over 2. And so this will be 1 over, and then we can rewrite this, well, I'll just write it here. This is 3 over 2 plus 1 in the denominator. We'll simplify it in a second. Minus, now, a function whose derivative is sine. The derivative of cosine is negative sine. So we can turn this into a plus 2 cosine of x. The derivative of cosine is negative sine. Plus, and now we have a c here. Now, very important, a lot of people just kind of stop there and go plus a constant. But this constant appeared at this level here. So we have to keep going. We need to come up with a function whose derivative will give you a constant there, so we have to introduce a term of c times x. Remember, we're looking for a function whose derivative equals to this boxed up one here, so we have to introduce that x there. And that means that we have to introduce a constant for this function. So we could, run into the notation of saying, well, let's make this plus c, but then that's confusing with that c and that c. So very often we can just subscript and say, well, let's call this c sub 1 and we'll call this one c sub 2. Perfectly great answer. And then that way, as we keep going, you can imagine we're going to come up with other constants. We can come up with c sub 3, c sub 4. So it makes it nice and convenient. So you'll find in a lot of places this is the result. They use little subscripts. But when we don't have too many variables, we like to stick to maybe using different letters. And I think that's what the author did here. So let's just stay consistent. So instead of naming that one c sub 2, I'm just going to name it d, some new constant d. Okay. I'm going to go ahead and leave the ones though, and I'll show you why in a second. C sub 1, like that. Okay, so now let's simplify this. This is f prime, so the first derivative then is equal to 2/3 times 1 over, and we said this is going to be equal to 5 over 2. So 5 divided by 2 times x to the 5 divided by 2 power, plus 2 cosine x plus c sub 1x plus d. Okay, I'm going to bring this up here and say f prime of x is equal to 2/3 times, and now to simplify this, we multiply the numerator times the reciprocal of the denominator. That'll be 2/5 x to the power of 5 over 2 plus 2 cosine x plus c sub 1x plus d. Okay, simplifying this, we end up with f prime of x equals to 4 over 15 x to the 5 over 2 plus 2 cosine x plus c sub 1x plus some constant d. Good. Okay, so next, finally, we get to the f of x that we wanted. All right, so let's leave this constant alone. We know that this is going to be x to the power of, let's make some more space there, x to the power of 5 divided by 2 plus 1. And then we need to compensate for that constant. So I know this is going to be a 2 over a 2. That's going to be 7 over 2. So I'm just going to go ahead and put 7 over 2 here. And then plus, and then a function whose derivative is cosine, we know that's going to be sine. That'll be 2 sine x plus c sub 1. Remember, that's just some constant. Remember, the pattern over here was to leave the constant alone and then deal with the exponent. Okay, so this has to be 1/2 x to the power of 2. Right? Bring down the 2, cancels with the 1/2, subtract 1, and that's how we get that x there. Plus dx plus, and now we need some other constant. Let's just use the letter capital E. Okay, so that means that f of x is equal to 4/15 times 2 over 7 x to the power of 7 over 2 plus 2 sine x plus, and I'm just going to switch these around, that'll be 1/2 c sub 1 x to the second power plus dx plus E. And then multiplying these, we end up with f of x gets me to 8 over 105 x to the 7 over 2 power plus 2 sine of x plus, okay, so this is why I left the c sub 1. We could leave this as 1/2 c sub 1, perfectly okay, but c is some number. It's just some constant number, and some constant multiplied by 1/2 just represents another constant. So very often you'll see that the answer is just this, c x squared plus dx plus E. where C, this is where the C is equal to the 1/2 C sub 1, right? So it's just some constant that belongs there. It just looks neater, and so very often authors just like to write it this way. Okay, so there's our answer. Well, maybe just to further emphasize, those constants, I should put where C equals to that, and of course, C sub 1, D, and E are real numbers, constants. Right? Just not an independent variable. That's all that's really important. Focus on the fact that x is the independent variable. All the other letters are constants in this case. Okay, now sometimes boundary conditions will be given so that you can identify the value of those constants. Let's try, for example, number 48. Okay, so given that the third derivative of a function equals to cosine of x, and that f of 0 equals to 1, and that f prime of 0 equals to 2, and that the second derivative of 0 equals to 3. Of course, this one says find f of x that satisfies all these conditions. Okay, so the boundary conditions, the values here, none of them involve the third derivative. So we can just jump right ahead and find our second derivative. So the second derivative is going to be equal to a function whose derivative equals to cosine of x. Well, that's just going to be equal to sine of x. And plus some constant c. Okay, so there's our second derivative. But we can find that value of c by implementing this information right there. We know that f double prime evaluated at 0 equals to 3. So that means that sine evaluated at 0 plus c must be equal to 3. Sine of 0 is 0. So that means that c must be equal to 3. Okay, so then we can come back over here and further specify that the second derivative must be equal to sine x plus 3. Good. Okay, so now let's go to the next layer. Let's find the first derivative. That means that the first derivative of x must be equal to a function who's equal to cosine, well, minus cosine of x will give me positive sine of x, right? So the derivative of cosine is negative sine, so we have to introduce an extra negative in front, plus 3x plus a constant. Now I could use c, but I've already used c before. It looks a little confusing. How about if we just move on to a different letter? How about d? Good. So here is that first derivative. But now we can use this information to help us further specify what that function is. So using that information, we say that f prime of 0, f prime evaluated at 0, which is going to be negative cosine of 0, plus 3 times 0 plus d, that all of that must be equal to 2. Okay, cosine of 0 is 1. This goes toward 1. 3 times 0, well, that's just going to be 0. So we get that negative 1 plus 0 plus d equals to 2. So d must be equal to 2 plus 1, or d also equals to 3. D also equals to 3. So we can combine that information to identify that the first derivative. So we can combine that information to identify that that first derivative is equal to negative cosine of x plus 3x plus d, but that d is now a 3. And you know what, actually I shouldn't have boxed up this one. I should have boxed up this one after we figured out the value of c. And so now we can box up this one, and now we have that first derivative as well. One more layer to go. Okay, so now finally we get to the function f of x. A function whose derivative is cosine, well, that's got to be sine. So minus sine x will give me minus cosine x plus 3 times 1/2 x to the power of 2 plus 3x plus some constant e. And again, we get to use this information right here, that f of 0 equals to 1. So f of 0 equals to negative sine of 0 plus 3 over 2 0 squared plus 3 times 0 plus e, and all of that must be equal to the number 1. Good? Okay. Sine of 0 is 0. That's 0. 0 times anything there, that's 0. 0 times 3, that's 0. So all of that really just leads to stating that e must be the number 1. Okay, so that allows us to rewrite our function and get the specific function. F of x equals to minus sine x plus 3 over 2 x to the second power plus 3x plus 1. And that's our final answer. Okay, so hopefully I've given you enough to get started on your homework. Please stop by my office hours if you have any questions.